Welcome to today's Explainer. We are skipping the usual fluff today and jumping straight into a massive paradigm shift, one that's literally reshaping our digital civilization as we speak. We are officially moving way beyond the era of isolated algorithms. Today, we're exploring what exactly happens when AI systems stop operating in a vacuum and actually start forming their own dynamic, interconnected societies.
So what does this all mean? Okay, let's dive into this. For the longest time, we really just thought of AI as a solitary tool, right? Like a single algorithm tackling a single, specific problem. But the recent research reveals a total game changer, a massive leap from those single-agent systems to incredibly complex, interactive AI societies. We're talking about multi-agent ecosystems where AIs collaborate, negotiate, deceive, and, no way, this is the crazy part, govern themselves entirely autonomously.
Here's our roadmap for the Explainer today. We'll start with the multi-agent leap, then look at simulating scientific discovery, navigating social dilemmas, cyber deception and defense, making AI transparent, and finally, securing the AI society.
All right, part 1, the multi-agent leap.
So the crucial point here is the huge contrast between the old way and the new way. In a single-agent setup, an AI just learns the best strategy to maximize its own rewards in a totally static vacuum. But let's be real, the world just doesn't work like that. The real world is a messy, distributed decision system. Multi-agent reinforcement learning actually forces AIs to share information, divvy up computing tasks, and coordinate their strategies. Sometimes they fully cooperate, sometimes they fiercely compete, and honestly, it's usually a really complex mix of both.
Now, to ground this mathematically, researchers use a framework known as Markov games. You can think of it kind of like shifting from playing a quiet game of solitaire to playing a massive, chaotic game of chess where everyone makes their moves at the exact same time. In Markov games, the state of the whole environment transitions based on the joint actions of all the agents simultaneously. This means every single choice an AI makes now mathematically impacts everyone else in the system. Your reward isn't just about what you do anymore. It's heavily dependent on what the rest of the AI society is up to.
Section 2. Simulating scientific discovery.
Now this next part is absolutely fascinating. In a recent study, researchers instantiated 2,686 AI scholar agents. These agents were powered by large language models and given highly specific personas based on the actual real-world publication histories of real computer scientists from before 2024. Then they took these 2,686 agents and dropped them into a massive simulation to see if they could collectively brainstorm and generate key research ideas for major 2024 computer science conferences.
And the results brilliantly illustrate how well this works. When you look at the distribution of ideas for major conferences, the AI-generated ideas align incredibly closely with the actual papers that human scientists ended up writing in 2024. It's practically a crystal ball. And here's a fun, surprising fact. The least predictable ideas actually came from simulated diverse teams affiliated with Chinese institutions, but not composed of ethnically Chinese authors. It really goes to show how these multi-agent simulations can genuinely model the evolution of human scientific knowledge.
Moving right along to part 3, navigating social dilemmas.
So when AI systems become a part of our everyday decisions, they inevitably run into situations where getting the best result for their specific user totally clashes with the greater good. It's exactly like climate change negotiations, right? Individual economic growth often conflicts with the collective need to cut carbon emissions. AI agents have to learn how to balance those short-term personal gains against long-term collective benefits. And honestly, this gets incredibly dangerous and complicated when agents start deploying sock puppets. Imagine a single AI creating dozens of fake, autonomous personas to artificially inflate its own side of a negotiation. It completely skews the collective benefit.
To train AIs to handle this, researchers test them in advanced environments. Things like Melting Pot 2.0. They put the agents through classic scenarios like the iterated prisoner's dilemma, grid world coin games, and even simulated climate change negotiations. And here's the kicker, if they fail these tests, the whole AI society collapses into selfish behavior. That is absolutely the last thing we want when these AIs eventually start managing our power grids or stock markets, right? The ultimate goal here is aligning individual incentives with the overall well-being of the group.
Section 4. Cyber deception and defense.
Let's shift gears and talk about modern networks, where defenders are actively using cyber deception. Picture an automated AI attacker cautiously probing a network. First, the attacker sends a SYN packet. It's basically a digital knock on the door to test the waters. Next, the defender's honeypot, which is a trap designed to mimic a legitimate service, replies. The attacker thinks, bingo, I found a vulnerability, and cautiously proceeds. But often, it's not just one agent knocking, it's a whole coordinated swarm of AI sock puppets probing the network all at once. Finally, the exploitation attempt is tracked. The attacker has unwittingly just handed the defender incredibly valuable intelligence about their own tactics.
To automate this kind of defense at a massive scale, defenders are fusing game models with foundation models to build something the literature calls guardware. You basically have game models handling the adversarial scenarios and security interactions, while foundation models, like your typical large language models, handle all the messy data, text processing, and predictive analytics. Fused together, this guardware becomes a proactive shield. It can actually predict what an attacker will do and dynamically deploy decoys to completely outsmart hackers.
Now, what's really interesting about this neurosymbolic setup is the continuous loop it creates. At its base, the system is constantly updating its best guesses or conjectures about the attacker's next move. That feeds right into the next layer, which updates security policies in real time. Above that, it tracks the broader environmental context, and right at the top, it updates the core knowledge base. It's this dynamic, never-ending loop that lets AI defenders stay one step ahead of zero-day attacks, simply by constantly learning from real-time cyber engagements.
Section 5. Making AI transparent.
Traditionally, multi-agent reinforcement learning leaned heavily on deep neural networks. But there's a huge problem with that. It creates a black box. You end up with millions of continuous parameters that are completely opaque. It's nearly impossible to verify, trust, or debug them. While the new solution is called Code Space Response Oracles, or CSRO. Instead of tweaking hidden math that we can't even understand, the AI now writes its strategy directly as human-readable source code. If an AI makes a mistake, a human engineer can literally just open the file, read the code, and see exactly why it did what it did. A real game changer.
This breakthrough leads to fascinating systems like AlphaEvolve. AlphaEvolve is this distributed, LLM-driven system that doesn't just generate code once and stop. It iteratively mutates and recombines functional code fragments to hunt down high-performing strategies. The agents are literally learning by rewriting their own digital DNA on the fly. Because of this, their logic becomes highly sample-efficient and, more importantly, completely verifiable to us.
Finally, Section 6. Securing the AI society.
We're finding out that centralized control is quickly becoming a huge bottleneck and a massive single point of failure. The latest literature points heavily toward decentralized safeguards. Frameworks like AgentNet allow agents to coordinate completely autonomously within a dynamic network. But, of course, when agents are constantly talking to agents, you risk errors piling up. That's exactly where systems like Guardian come in. Guardian explicitly tracks and halts the spread of errors across the network. Because let's face it, the very last thing you want is one hallucinating AI convincing a whole network of AIs that the sky is falling. Plus, it's absolutely crucial for stopping those malicious sock puppet swarms we talked about earlier from hijacking the system's consensus.
The ultimate goal highlighted across all these papers is super clear. We need to build a fault-tolerant, self-governing ecosystem that scales without humans having to micromanage every little detail. To quote the research directly, AgentNet enables agents to autonomously evolve their capabilities and collaborate efficiently in a network, removing the central orchestrator.
Which leaves us with a pretty profound realization. We've seen how these systems are shifting from isolated tools to collaborative, code-writing, highly strategic societies capable of simulating future research and autonomously defending our networks. So I leave you with this question to chew on. If AI can now reliably simulate our scientific discoveries and negotiate our most complex social dilemmas, what exactly is the role humans will play in the loop of this new autonomous digital society? Thank you so much for joining this explainer. Keep questioning and keep learning.